All right. So this time I am actually recording. I thought I was recording last Thursday, and I think I missed one of the steps. Probably did not click the button. But today is going to be recorded. All right. So um, we have a sample program here that uses your structure, and we are going to translate this program into TTP ASM today. This one is ar.c, which is one of the links, from Canvas. So the C code, is available. You can download it anytime you want. And then what we'll do today is to really kind of implement this in assembly. And I think this one is complicated enough that I'm bound to make some mistakes at some point, which is great because that is what I really want to demonstrate because you're gonna get a new programming assignment today that is due next Tuesday. So you got a week to work on it. How you do it is the key. Okay, if you're expecting yourself to be able to write the entire program in one shot and get it right the first time, um, then you are a much better assembly language programmer than I have ever been. Okay, which is entirely possible. Okay, that's entirely possible. Um, if you want to rely on the AI tool and expect it to also give you the correct answer, um, that may not be the truth. Okay, it might be able to give you kind of like a outline of how to do things, but I really doubt that it can give you the exact code. Simply because of the probabilistic nature of LLMs. Okay, so that's kind of what you need to learn about LLM is do they have limitations? Can I still get a job when I'm done with my education? All right. So it is about the approach. Okay. It is about, how do you debug your program step by step? Okay. That's the key is doing things in a step by step manner. And before that, you kind of have to understand all the basic concepts behind what we are doing now. So what we'll do is we'll take a quick look at the C code first and see whether there are any questions about the C code itself. So we're just doing quick scan of the C code. I think line 1 to line 12 or so are stuff that's is stuff that we have already talked about on last Thursday, so it should not become as a big surprise. And then on line 13 we have a double asterisk. It is a function that returns a pointer to a struct node. Okay, so do we do we feel comfortable with pointer to a pointer as opposed to just one single pointer? If you understand a pointer, then a pointer to a pointer is just one more dereference. Okay. And then we get to line 15, which has we have a local variable called the result, and it is a double pointer. Okay. And it's also going to be the return value. On line 16, or I would say line 16 is probably one of the most difficult line to parse and to figure out what to do. Well, the first thing, so when we disassemble these things, or when we deconstruct the original C code, we have to think about what is the order of doing things. Okay, so the first thing we recognize is this is a logical OR, so that means it's mandatory that we have to evaluate from left to right. So the first thing we need to evaluate is the left-hand side, which is not really super duper complicated. The right-hand side looks a little bit more complicated because it is using member value of the structure that is pointed to by a unnamed pointer that in return is pointed to by ppn, which is a parameter. So how you articulate, okay, the statement or the expression is the key, okay, because once you know how to articulate it correctly, then the way you articulate it is going to be, the guide of how to turn everything into assembly language code. Um, the right-hand side of the comparison, that's something that we have already talked about. So for the most part, you can borrow the code from the lecture on Thursday, okay, which unfortunately was not recorded, but you still have the source code. So I hope some of you, well, okay, I hope all of you had the time over the weekend to comment that program, or at least go through the program and make sure you understand how it works. Okay. Um, And then we get into the actual code here. None of these is super duper difficult. It's just that you have to pay attention to what you're doing, and once again, be able to articulate precisely and correctly what needs to be done. So I would say your understanding of C and C++ may be even slightly more important than your understanding of assembly language programming. Okay, and that's why CISP 360 is a prerequisite of this class. And that is also why I feel really bad for people who have a background in Java instead of C++. Because depending on where they come from, okay, some of the other community colleges and Sac State, okay, they only use Java for the most part of their classes. They don't teach C++. So the whole concept of a pointer to a pointer can be a little bit difficult to understand when they understand are references. All right, so that's about it. Main is pretty not exciting. Okay, so we can go take a look at main in this case, and you can see that main is totally mm, meh, not interesting. Okay, just three function calls to F. That's it. All right. So, do we have any questions about the C code? Because if you are looking at the C code and squinting in your mind, we might need to get that squinting addressed. So nobody is squinting internally or externally. We all good? All right. Okay. How many people have taken CISP 400 already? So we got two or three. Okay. So five maybe. So the rest of you may actually benefit from this class as a preparation for CISP 400 as well as 430. Because in those classes, you have to come up with code like this. But in this class, I give you the code, and we're only concerned about translating that into assembly language. So the scope is entirely different in this class. All right. So what we'll do is we're gonna do a V split, okay, and then on the other side, we'll work on the ar.ttpasm, which is the source code, and in this case, I have most of the other stuff done already. We just have to implement function f. Okay. But I'll explain everything too. Okay, this is our typical entry code. I suppose we should initialize the stack pointer as well, even though it is not necessary. The reason why it is not 100% necessary is because the stack is always or the stack pointer is always reset to 0 when we power up the processor, okay, so to speak. But it doesn't hurt to put a 0 there just so that we got that addressed. Lines 9 to 11 correspond to the definition of the structure, which is on line 3 to line 7 in the C code. We have two members only in this case. We have P next, which is the first member of a struct node. So that's why it is at an offset of 0 from the beginning of a structure. And then the next member is called value. And that's why the offset from the beginning of the structure to find the member value is basically where we find P next and then plus the size of P next itself, which is on line 10 of the assembly code. Node size is basically trying to figure out what is the size or how many bytes do we need for a struct node. So that would be taking the offset to the last member of the structure and then add the size of the last member of the structure. And that's why we have node value 1 plus, which is a postfix notation or RPN. All right. So do we have any questions up to line 11 of the assembly code? This should be pretty much a review of the code that we looked at on last Thursday. So we are good. Okay. Then we move on to lines 14 to 21 of the assembly code on the right-hand side. So that's basically how we initialize N3, N2, N1 as global variables. We have done this already last Thursday as well. Okay, so all global variables, do not belong on the stack, and instead we just use the byte directive to initialize those global variables, and then the labels N1, N2, and N3, are actually representing the address of those individual global variables. So we talked about that as well, I believe, on last Thursday. Is that correct? Okay. All right. So what we need to do at this point is to basically implement the function f. Okay. But before we do that, it might be helpful for us to take a look at the main code. Okay. So I'm going to go to main, like so, and also to go to the C code in main. Um, all right, so we have only one single global variable in this case, excuse me, local variable of main, which is called p next, p first. So p first is a local variable of main, and we can see in the C code that it is a pointer to a struct node, which in assembly only takes 1 byte. So that's why LBS of main is defined to be main p first 1 plus, because your p first as a pointer only takes 1 byte on the stack. And then we recognize a lot of the things that we have talked about. On line 30 to line 31, we allocate for the local variables, and then also at the very end, we deallocate the local variables all the way down here. Okay, and this is the usual code to return to the caller after we deallocate the local variables. Okay, so other than that, the entry point and the exit point of main is not exactly very exciting. Okay, so we get into the itty-gritty details of main. From line 33 to line 36, we are implementing line 32 of the C code. And then on line 38, it is the first line to implement the call to F. So not really a whole lot of exciting stuff happening here, except for the 1 plus on line 41. So because we have to push the arguments um, in a reverse order, which means the last argument is pushed first. So that's why we have to push N1 first. So even though in the C code it is the address of N1, the label N1 is actually representing the address already, and that's what we need to push. So line 38 to line 40 is pushing the address of N1 on the stack. That's not difficult. But when it's time to push the address of P first on the stack, we have to put in this little 1 plus here, because at that time, the stack pointer is no longer pointing to the base of the frame. It is pointing to 1 byte below the base of the frame. And the label main underscore P first is relative to the beginning of the frame. So when the stack pointer, register D, is now pointing to 1 byte below where the frame starts, okay, we have to compensate that for that 1 byte in some way, okay? So you can not have the 1 plus here, and then you'll have a um, increment A either here between line 41 and 42, or between line 42 to line 43. That will do the same thing. But having an increment A instruction is taking extra execution time when it's not needed, because we can just add one to the constant of LDI on line 41 and get the same thing accomplished. So are we all understanding why there is a 1 plus on line 41? It has to do with the assumption that the stack pointer is pointing to the base of the frame was no longer valid. We just pushed something right below the base of the frame. So are we okay with that concept? So this does require you to understand, what is the frame of a function in a function call, what is the purpose of the stack pointer, and typically where the stack pointer points to when we're in a function. Okay, so all of those things are actually kind of important in order to understand why the one plus is necessary. So I'm basically spelling out for those people who are mentally squinting. I'm just pointing out, what topics to review in order to fully understand why that one plus is necessary on line 41. All right, so and then from line 41 to line 44, we're pushing the address of P first on the stack. Line 45 to line 47 is pushing the return address on the stack. We do the call on line 48, and then on line 49 and line 50, we deallocate the 2 bytes of arguments from the stack. So all of that is pretty much the stuff that is coming straight out of the caller callee agreement, and also sample programs that we have already examined in the past. All right, so we can now continue. And this is just basically the same thing, except we are pushing N2 instead of N1, and then we push N3 instead of N2. So that's kind of a whole lot of repetition over there, okay? Because when you look at the C code, lines 33, 34, and 35 are pretty much the same, except for N1, N2, and N3. So are we doing okay so far with all of this? Okay. Questions? No questions? Okay. So even though you have no questions, I am going to demonstrate how the C code is going to work because I think that is also kind of important. So what we'll do is do a gcc-g-o ar.c gdbar, and I need to find a good place to put a breakpoint. Let's put it on line 33. Here we go. So we run the program until this point. Essentially, this is what we call a linked list, okay? And P first is the head of the linked list, okay? Um, and then once we execute, so N is called next, okay? What it does is it will stop after the function call on the line that I'm dealing with right now. So what that means is because I put a breakpoint on line, what was it, line 33, so if I put a step, if I use lowercase s, it would actually stop inside the function so we can actually see how everything works. But I just want to show you the effect of calling the function. So I'm going to use next so that it stops at the next statement in the same function. Okay, there we go. So now we are ready to call f again, but using n2. But before we do that, we're going to say, okay, show me what is p first. So at this point, p first points to n1. And then we say, okay, show me the structure that P first is pointing to, and we can see how P first has a P next of null, which means it is the last item of the list. If we do another next, it would put N2 onto the linked list, and I cannot remember, whether it is attaching it to the front or the end of the linked list. So I guess we'll find out. Okay, so print P first. Okay, so N2 is actually now becoming the head of the list or the first item of the list. But when we look at N2, okay, or whatever P first is pointing to, because they're the same thing, we can also see how N2 is now pointing to N1. So we have basically a chain. P first points to N2, and then the P next of N2 points to P1. Okay, so now we have a little chain of pointers so that we can have access to both N2 and N1. We're now ready to call F again on line 35. So you can probably imagine what this is going to do, right? So P first will end up pointing at N3. The P next of N3 points to N2. The P next of N2 points to P1, N1. And then the P next of N1 points to null to basically signify, yes, I'm the last item of the linked list. But we're going to do that anyway, okay, just to be sure that we know what is happening here. Okay, so everything is done at this point. So we're going to do the same thing. Okay, we look at what is P first. Okay, Oh, it is okay. I now know. Okay, it maintains a sorting order. Okay, I take it back. It's not just you're putting things at the beginning because otherwise that would be way too easy. So it is maintaining a sorting order as well. Okay, so we can now take a look at what is the value that P first is pointing to. It is a 2. And now we can say, okay, what is the next item? Uh, so this is the first item. This is the address of the second item. This is the value of the second item. It is a 4. So you can probably imagine that this becomes the third item, and this becomes the value of the third item, and it is a 5. So it is actually making sure that the linked list has the values in increasing order. So it's doing sorting and attaching new items to the linked list at the same time. Are we doing okay so far? Can you form a mental picture of what is going on, more or less? Okay. Does anyone want me to draw a picture on the whiteboard? Okay, all right, we can do that. So basically, we have P first, okay, which is a pointer pointing to a structure. That structure is what we know as N2 as a global variable. And then the value of N2 is already fixed. We never really change the value, which in this case is 2. And then the first member of N2 is P next, which is a pointer. That pointer in return points to another thing over here where the value is 4, and that would be N3. Okay, so this is N3. And then the P next of N3 in return points to another structure, which in this case is N1, the global variable N1, which has a value of 5. So technically speaking, this does not go anywhere. So I'm going to use a ground symbol to represent that it is not going anywhere at this point. Question? Because that's what F does. So F has to traverse the linked list until it finds the right place to insert the new node. Yes. So it won't insert before a node when the value is greater than the value of the node, or when you're at the null pointer. So when you're at the null pointer, then it goes like, hey, uh, I'm going to put myself here because nobody is there to compare to anyway. So I'm going to have to attach it there. So there are two conditions to be attached to the linked list. Yep. All right. So this picture is kind of important, okay, to understand the algorithm. But our focus is not, linked lists or data structure. Our focus is really, looking at the C code. How do we translate that into assembly code? Okay, so that's our focus in this class. I think taking this class first before CISP 400 has a certain advantage because now that you have a thorough understanding of what pointers actually do and what the linked list actually look like in memory, when you take CISP 400 and 430, I think you actually will find it a little bit easier because otherwise pointers is a really kind of abstract concept, right? What does it mean to have a pointer or to take the address of or to dereference? In this class, we actually boil everything down to the instructions. And only two instructions have to do with memory access, either a load or a store. Okay, so we are looking at the very elemental level of accessing things. When we are actually looking at the high level code, we're translating that into low level code as low as it possibly can be in from the perspective of a software engineer. All right, so I think we are good to keep that picture around. Okay, so now we can kind of get out of the C code, go back to the editor, and then start to implement F. unless anyone has a question. Okay, so if you have a question, go ahead and ask the question. So I put a halt instruction here just so that I can examine what is in memory. Particularly, the important stuff that is in memory is where's N1, where's N2, where's N3, um, where is P first in memory, and so on and so forth. So that understanding is also really important. So what we'll do is we're going to draw the stack. I will draw the stack on the whiteboard. We start at location FF, okay? Then we have FE, and then we have FD, we have FC, we have FB. I believe that is all we need when we put a halt instruction on F, okay? This is the usual, which is the return address to the entry point, okay? So that has not really changed much, since a long time ago. FE is our P first, okay? In other words, this item here, this guy here, is at location FE. We good so far? Okay. And then we push the two arguments on the stack. The first argument that we push was what? N1. Okay, so this is basically the address of N1, which is labeled N1. And I cannot tell you what N1 is, just by looking at the code. I suppose I can do some counting and actually tell you, but it is a little bit of work, but I can do it too. FC is going to be, okay, let's check out what FC is. So at location FC, it is the address of P first. It is not the value of P first. So P first, okay, which is what FE is representing, has a value of zero. No, yeah, it has a value of 0, 0 at this point. Okay, are we understanding the difference between where it is and the value at that location? So we are good? Okay, all right, because that is actually important. So FC is not going to have 0, 0 because I'm not pushing P first on the stack. I'm pushing the address of P first on the stack. So at location FC, it should have a value of FE instead because it is the address of P first. Is that clear? Okay. And then FB has a return address. Okay. So this is just a return address back to main, which this one is actually a whole lot of hassle to compute it by hand. So we're going to use the assembler a little bit to cheat so that we can figure out the return address C's. But otherwise, I think that's what the stack should look like when we at the halt instruction. Where do you think the stack pointer is pointing to? That is a caller callee agreement kind of thing. So when the caller pass control to the callee, where is the stack pointer pointing to? The return address. Very good. So that means register D should be pointing to location FB. All right. So now we are going to actually run the code, okay, and see whether that is what we see, and then we can also resolve, what is where's N1, N2, and N3, and that sort of thing. So I'm going to use this window, go to the folder CSP310 River Spider, and then just run it from here. Okay, so this is what ar.ptp and I can tell you that if you want to get the homework assignment done at this point of time, you can still do it without River Spider. I could have done that without River Spider, but I think with River Spider, it can save you a tremendous amount of time. Okay, so it becomes kind of important to do that. All right, so we got everything, and then we can now switch back to the assembler and then go to the analysis. Well, before we get to the analysis tab, okay, I do want to take note of where is N3, N2, and N1, and this is actually what we are seeing right now. There we go. So I can just kind of write down N3 is at location 08, and then the N2 is at location 0A, and then N1 is at location 0C. Okay, so I can just write down here. This is at location N2 is 0A, Okay, so we can say this is at location 0A. This one is the first one, which is 0, 8, and then this one is 0C, like so. Okay, so these are the addresses of N2, N3, and N1 respectively. Are we good so far? So I'm identifying where everything is. Okay, PF or P first of main is at location FE, which is on the stack. These three items are not on the stack because they are global variables. Are we doing okay so far? All right. And then we can also resolve the return addresses. The first one is, I'm pretty sure it is 09, okay? The reason why I know that is because the entry code really hasn't changed too much, or in this case, it is 07. Okay, why is it 07? Did I miss something? Oh, okay, I know what's happening because this is before I forgot to save the code first, okay? Because remember, I put in the extra code to load a 0 into register D. That program was not saved. Okay, that was kind of classic of what I usually do. Okay, that's fine. Save it first and then rerun the code up to the halt. Okay, there we go. But you can also tell that every time I see something that is suspicious, I stop, okay, and I try to explain that right away. I don't just go like, well, but the rest of the program seems to be okay. We can just proceed, okay? I do not have that kind of mentality. I really have to explain everything before going forward. So now I go like, okay, now I feel a lot more comfortable because halt is now at where I thought it should be, which is at location 09. So location 09 is the return address to the entry point. So that means, FF now has a content of 09. And I can also just kind of look up where the other one is supposed to be, but that's not like super important because it's going to change as we add more code to the program. But we can still at least find out for this time just so that we don't get surprised if it is not getting back to the location where it's supposed to be. So this is the return address. Nope, not this one here. So 29, not 29. 29 should be the return address back to main. So I should see a 29 at location FB. Okay, so now I have a full map of what each location of RAM should have by the time we get to the halt instruction. Okay, so that means, I can actually do all of this verification even without using River Spider. I can run the whole program only in Logisim, okay? Because the hold instruction will automatically stop the execution, right? So you just look at the memory content in RAM and make sure that those locations have those particular values. That is one thing that I think everybody should do if this was the homework assignment, but it wasn't. Okay, this is a makeup homework assignment for myself for this class, like this session. All right, so now we can go to the analysis tab and only focus on what memory locations are overwritten in what way. So FF is getting 09 as expected. FE is getting 00, kind of as expected. FD is getting the address of N1, which is now at 0E, because when I added the LDI D0 instruction, everything got shifted down by 2 bytes. So 0E is exactly 2 bytes after 0C. Okay, so that's correct. So everything is going to be shifted by 2 bytes down, in terms of N1, N2, and N3 as a result of that. So I should probably correct it, okay, just so that they're correct now. This is now 0A, and this is now 0C. There we go. Because it's good to keep the picture consistent with what we should be seeing. And then we have one more thing, or we have two more things. FC should get FE. So, yep, so that's all good. And then FB is getting to 9 as expected on the whiteboard. So now I feel comfortable proceeding with actually writing the first line of code because I need to know Am I understanding the arguments correctly? Okay, and this is a good verification that I have a consistent understanding between the C code and how the program should behave up to the halt instruction. Are we doing okay so far? Okay. It is about the approach. I think the approach itself is just as important as the concepts. Okay, because if you people who are taking a shortcut approach um, would probably not understand the concepts either. Okay, so it has to people have to slow down when they're not really sure what is supposed to be happening. Then they have to slow down and go like, okay, and is my understanding correct? All right. I'm just looking at the watch to make sure that I have enough time to finish this whole thing. All right, so we are now going to implement F. And the way we do it is, the way I do it, okay, is to define a bunch of labels first. So we are going to start with the local variable result, okay. We only have one local variable here, so the order is not even that important. This is going to be at the base of the call frame because it is allocated by the function itself, so it has to be at the lowest location. And then LVS is just going to be F result plus the size of result itself. Okay, result. There we go. It is a pointer of some kind, so all pointers are only 1 byte long. The fact that it is a pointer to a pointer means it is still a pointer, right? So any pointer is only going to use a 1 byte. All right. So now we can move on to the parameters. PPN is the first parameter. It is going to be FLVS 1 plus. So this one is accounting for the return address, okay? Because you have all the local variables at the lowest portion of the call frame, and then the next item is the return address. And then the following item, if any, would be your parameters. So that's why we still need a 1 plus on line 26 in order to account for the return address. And then we have f underscore pn, okay, which is our second parameter. It is going to be fppn 1 plus. Okay, there we go. So all of these labels are giving us symbolic access to the various items that we need when we actually write the code. Okay, and that is kind of important. So you can double check whether these are all correct or not. Because result being 0, okay, this is before we do the allocation, we can't see it. So we have to do the allocation, and all that crap first, and then we can get to see, why the offsets make sense. Okay, so that means we have a LDI with F underscore LVS, subtract that much from the stack pointer to do the allocation. And then the deallocation is going to be the reverse of the operation. We are adding to the stack pointer instead. And then we have the usual LDBD increment D and then JMPB over here. Okay, the halt instruction is still here because I want to see whether the offset, okay, makes sense or not. So we are going to kind of check out everything because at this point, what we should see on the stack is we have something at location FA. I don't know exactly what it is. Okay, we just know that there's something there. But the stack pointer at the halt instruction will now be pointing to the FA. FA is result as a local variable of the callee. This is the return address. This is our PPN. This is our PN. So PN is the name of location FD from the perspective of the callee. Okay, the function being called, look at the location FD and say, hey, that's my parameter PN. FC at the location FC, from the perspective of the callee, it knows this as the parameter ppn. But from the caller, okay, location FD is the address of N1. From the perspective of the caller, location FC is known as the address of P first. So are we doing okay so far, understanding that each location has essentially two names? One is coming from the caller as an argument. The second one is as a callee what is the name of that parameter. Are we understanding that concept? Okay. And that's why the caller calling agreement is so important, because they have to have this understanding so that they understand what each location is representing. That part has to be agreed upon, because otherwise the caller can push a bunch of stuff on the stack, right? And then the caller goes like, I have no idea where you push which item where. So I'm just going to use my own ordering to access those items. That's not going to work. Okay, so are we still good? Okay, all right. So now we just take a look at, okay, are the offsets correct? Result is 0. Okay, that's good because that's exactly where the stack point is pointing to, and this is the base of the entire frame. So when we look at the frame of F, okay, consists of all of the parameters, the return address, and all of the local variables. That is the frame of F. So the frame is also called an invocation frame or a call frame or just frame itself, but they all represent the same thing. Okay, what does the function need to get its job done? So result has an offset of 0. Okay, ppn should have a offset of 2. So does it actually have an offset of 2? This is 0. This is 1. This is 2. Okay, that's cool. What about PN? It should have an offset of 4. Do we have an offset of 4? Well, PPN is already a 3. PN being PPN plus 1 is going to be 4. So I think all the offsets are correct. All right. So I am actually repeating a lot of stuff that we have already talked about in today's class. So I'm hoping that this will help people who are still trying to kind of get a foothold of understanding all the material. So this lecture is kind of having a little bit of repetition of your content from the previous lectures. All right. So now we can go like, okay, we can now start to implement the code. So we have to first check to see if um, the pointer that is pointed to by ppn is null or not. The, uh, the, the, the address, I should say, the address the ppn is pointing to, whether it is null or not. So what we're doing is we're asking ppn to say, hey, show me where you point to. I'm pointing to location fe, and then location fe has a value of 0 0. So in this case, the first the left hand side of the disjunction should be a true, because ppn itself is not null. Ppn itself is fe, but what it points to is null. So when you say not null, okay, it is saying not false. Not false is going to be true. Okay, so we'll go ahead and just write the code, okay, right here. So we have LDI, pick any one of the 3 registers. It doesn't really matter which one at this point. We'll use register A. Okay, F underscore ppn, add AD, and then we have LDAA, and then we have another LDAA. So I'm going to do LDBA at this point because I might want to save ppn, the value of ppn. So I'm going to save it into a separate register because I have all the registers available to me right now. So it doesn't cost me anything to do this. All right. So now you have to think in your head, okay, what is in each register at each point of the code from line 32 to line 35. This is the offset. This is the actual address of ppn. This is the value of ppn. This is what ppn points to. Okay, I just said a whole bunch of stuff. Okay, so let's just say that I'm kind of shaky with all the material in this class. In fact, I'm kind of shaky with my CISP 360 concepts. What am I going to do? Run the code right now. Rely on the halt instruction and verify that the 2 registers A and B, in fact, register A has ppn, which is fe, Register B has what it points to, which is 00. Okay, that's all I want to verify. Okay, so we'll save the code first. Okay, because I have a tendency of forgetting to save the code before running it. There we go. At some point, I'm going to have to write some script to turn Vim into its own IDE, but not this semester. I got some unpleasant surprises this semester to deal with. All right, so now we are ready to kind of test the code. So we can kind of fast forward. Okay, so we just need to know what is in each register by the time we get to the halt instruction. Register A is supposed to have the value of ppn. So according to the whiteboard, ppn has a value of fe. That's all good. And then register B is supposed to be what ppn is pointing to. Well, since ppn is fe, it points to location fe. Location fe currently has a value of 0, so we're expecting register B to be 00, which is also verified in the trace. So this is why I actually put in some time to make the trace possible, with this tool, because this is how you can actually see the sequences of the updates of the registers and be able to look at how each register changes over time with the individual instructions and understand what each instruction is doing. Okay, which also means, if I don't change this, spreadsheet by the end of today, you can take a snapshot of it. Okay, go to File, save a copy, and then change the name. Okay, and then you can annotate all of these rows and with additional columns. You can use column H, as a kind of verbal description. Use column I to refer to the C code, of what it is supposed to be doing in the C code, and so on. Okay, this is a tool, okay, for you to fully understand what is going on when these programs execute. What I haven't tried, okay, which is something that you can do, is to download the spreadsheet like this and give the AI a certain explanation of what each column is representing, okay, and then upload all of the other stuff that we have in this class, and then have the AI to actually try to explain what each instruction is doing. That I haven't tried, but I'm suspecting the AI can actually do that already. Okay, so that's something that you can try. Okay, but I don't have time to give that a try this semester. All right, so we are all good here. So that means that we can continue with our coding. Okay, all right. So by this time we have asterisk ppn already figured out, and we are basically saying, hey, if that is actually 00, let's do it. Okay, let's go to the then portion of the conditional statement on line 18. Okay, because it's an or, right? It's a disjunction. If the left-hand side is already true, we just go straight to the then statement. We don't have to evaluate, or we should not evaluate the right-hand side because of the lazy Boolean expression evaluation. Okay, so now I go like, okay, let's do it and BB. If it is a 0, we go to the then portion. So the way I name my label is a little bit verbose, okay, but there's a reason, okay. So we have to go to the then statement, the first then statement at the top level of function f, okay. That's what this means. And I'm going to define the label here, f then 0, okay. And because I'm notorious of forgetting the context of a label, okay, I'm just going to say corresponding to line 18 of the C code, because otherwise, by the time I get to that code, I might have forgotten what it means to be at that label. Okay, this is also a great time to explain, how we do things is different from how AI do things. We have a short-term memory of about 5 to 7 items, and short-term means 20 seconds or so. Okay, so that means the kind of code that we can work on, or which portion of the code we can focus on, is really limited. AIs, on the other hand, they usually have a context window these days measured in millions of, at least a million mega of token. One token is a word. So that means they can do correlation, within a million words and punctuations without a problem. That's quote unquote its short-term memory. So if you're trying to compete with AI in terms of short-term memory, don't even try. Okay, there's no way we can do this. It's kind of like asking can you run faster even a slow car these days? Okay, the answer is no. There's no way you can outrun a car, or even a bicycle. So you have to understand the structural advantage of the tool and make sure that you don't try to compete, based on that. Okay, so you have to find something else to compete. Okay, you have to find something else where you can do it a better job than the AI. So I think it's just me interjecting, kind of my view on AI, okay, and how humans are different from AI. All right, so now we can continue with this code and just go like, we can finish the rest of this code, but I'm gonna say do this later, okay? Because I like to procrastinate. But more importantly, I know the first time we call this thing, it should not even be here, okay? So I'm gonna put another halt instruction here just in case I made a mistake, okay? So I'm gonna put a halt instruction here and say we should not be here. Okay, so now the question is why? There are two halt instructions right now. One is on line 40, the other one is on line 45. According to the C code, why do you think we should not end up at line 40 and we should end up at line 45 instead? They're not sorted already. Okay, we are just we are making the first call, right? Because of the halt instruction and program is or the function is incomplete, we cannot be doing recursive calls. We're not even returning from the first call. We're just kind of be stuck somewhere within the first call. Within the first call, p first has a value of 0. So ppn is the address of p first. So what ppn points to is the value of p first. But p first was initialized to a 0. So that means when we look at the asterisk of ppn, it is a 0. Not 0 is true. So that means I should not have to bother to look at the rest of the expression on line 16 in the C code and go straight to the then branch right away. So that's how I analyze the program and go like, oh, okay, we should end up on line 45 as a halt instruction, and we should not end at line 40. So running the program as it is right now is actually important because it tells me that yes, when ppn or what ppn points to is null, I'm going into the then branch correctly. Okay, so that's what I'll do. Okay, make sure I save the code first and then run it. So once again, I'm illustrating the approach of writing your assembly code step by step for the homework assignment. Okay, so it's just as important, I think, as the actual concept that you need to use. Kind of go hand in hand. All right, so we're gonna go, until it halts. Okay, so this is the halt instruction. I know that we are at the right halt instruction because it doesn't say that we are not supposed to be here, and this is also line 45. So the trace is super helpful because if you do end up on the wrong line, okay, then you have to ask, why am I here? The trace gives you full documentation of how you got to line 43, if you got to line 43. So that means you can execute a program quote unquote backwards and find out exactly how you got onto the wrong branch ending at the wrong halt instruction. A C debugger does not do that. Okay, a C debugger cannot give you a trace of anything. It can get you to a breakpoint. Okay, it pauses its execution, but how you got there is not documented. Okay, but this tool does give you full documentation of how we got here in the first place because the JCI branched because the Z flag was a 1 The Z flag was a 1 because of the AND BB instruction. The AND BB instruction gave us a 0, or the Z flag being a 1, because register B is 0. And register B is 0 because uh, it is what PPN is pointing to. So we do okay so far in terms of understanding how to look at this trace and use it to tell you how we got to a certain point. Is that okay? So I'm going to have to say that reversing the execution of code may not be something that the AI is very good at. I think a person can do this better, kind of going backwards to explain something compared to an AI. Don't do it now because you have your final exams, okay? But after your final exam, okay, take some of my programs, mess it up intentionally, okay, and then give the trace to the AI and see if the AI can figure out what problem you introduce into the code that causes the problem. Okay, because from my perspective, it is just out of curiosity. From your perspective, you're trying to differentiate what you can do that the AI cannot do. So that experiment becomes even more important from your perspective. All right. So now that we got that part done, okay, we can now continue with our coding. Okay, so that's all good. If you're using or GitHub to kind of do revision control, I would save this program. Okay, I would save this code and kind of leave behind a little comment to say that okay, I think I got the left hand side of the OR on line 16 done. Okay, just so that you have a place to fall back on when the program just completely stops working altogether. All right, so we are going to take out this halt instruction and continue with this code, okay? So this would be the right-hand side of the OR, okay, which looks horrendous, okay? Just look at all the greater than symbol. So what you need to do in your mind is to go like, okay, what do I need? What is the order of doing things? Well, I need to get to the left-hand side of the comparison. I need to get to the right-hand side of the comparison, and then I need to compare. So how do I get to the left-hand side of the compare? Hmm, it looks like since we already have whatever ppm points to in register B, that saves us some trouble, right? In other words, what the left-hand side of the compare is trying to do is to get the value of the member called value of the structure that the pointer that is pointed to by ppn is pointing to, okay? But we already have whatever ppn is pointing to in register B, because otherwise we wouldn't be able to get to the if the then zero label correctly. So that means what is left to do is, oh, okay, we have the address of the structure already. We just need to go from the address of the structure to the value of a member. Well, it's not as bad of a task, okay? So we have to keep B around, okay? Register A does not seem to be useful anymore because it is just the address of ppn, which we don't need for a while. So I can reuse register A now. So I'm going to load node underscore value into it, which is the offset to find the, the member called value. And I just have to add register B to register A because I want to keep register B around for as long as I possibly can because that seems important to me. Um, so now register A should have the address of the member value of the structure that is pointed to by a pointer, which in return is pointed to by ppn. That articulation, as tedious as it seems to be, is important because there are many people who say, "But Tech, aren't you a little bit anal about you know, spelling out what needs to be done?" The answer is you have to be able to do that in order to translate the code to understand what exactly is going on. All right, so I'm going to do LDAA here so that we can actually get to the value of the member value, which is supposed to be what? Since we use N1 first, so that should be a 5. Okay, so at this point, register A should have a value of 5. So I'm going to put a halt instruction right here and say that. Okay, so we say halt, reg A should be 5 at this point. Save the program, run it again. I don't know how to convey um, the systematic nature of how to write code. Okay, I can emphasize how important it is. I can illustrate how I do it, but I cannot otherwise articulate the structure of doing things in a systematic way. All right, so we are I ran it. Yes. Okay, so we have to check register A. No, that's not the right code. Okay, what happened? Did I forget to save the code again? No, I think I saved it. Control G. Yep, I saved the code. Oh, okay. I know why. Because we're supposed to go to the then statement. So this part I cannot really test right now because P first is a null. So I'm forcing it to not to get to here. All right. Well, that means I can write a bunch of code here, and I can't really test it at this point. So I will still finish the code so that when it is time to test it, I can test it. I will keep the halt instruction here. So I'm done with specifying the left-hand side of the greater than. I just need to get to the right-hand side of the greater than. So I'm just gonna you know register A is the left-hand side of the greater than of line 16. Because if I don't say that, I'm going to forget what register A has. All right, so let's go figure out the right-hand side of the comparison. It is supposed to be the value of the structure that is pointed to by Pn. Okay, so that's a little bit easier. So I want to keep register A. I absolutely need to keep register A around. I want to keep register B around, but I don't think I have enough registers to not to do that. So I'm going to have to use register C first. Just, you know, hopefully we don't have to get to register B, but I think I'm going to have to get to it anyway. So LDC FPN, add CD, get to the address, a LDCC. This is PN itself, and then we have to get the offset to value. So this is where I have to reuse one of the registers. I cannot reuse register A, so the only one I can reuse is register B. So register B is going to be node underscore value. Add those two. Doesn't matter which way. So add CB. Yeah, doesn't matter which way. So register C now has the address of member value of the structure the PN is pointing to. So I need one more LD instruction to get to the value itself. So now register C is the right-hand side of the greater than of line 16. So I know I need a compare instruction. The question is, which way do I want to compare? So since we're trying to confirm that what PN points to is less than what uh, the indirect of PPN points to, so it kind of makes sense to do a subtraction where I use the right hand side, which is in register C, and then subtract the left hand side from it. So we're gonna do a CMP CA and then do a JLI to the then statement to what is it, f underscore then 0. And if not, we are going to have an unconditional branch to the else branch, okay? Because we have just exhausted every possible way to end up um, with the then branch. So if that doesn't happen, then we have to go to the else branch. So now we go to the else branch, which is f underscore else 0. So then I'm going to write that code right here. Okay, f underscore else 0 goes here. But right before, I need an unconditional branch of the then branch to go around the else branch. So this is going to be going to the end if label, and then the end if label is going to be here. There we go. So what you can see is I'm writing this code in a structural way. Okay, I'm not just writing it sequentially. I'm writing it in a very structural way. As it is right now, we are going to line 58 right after the left-hand side. So there's no actual way for me to test whether this part is working or not. Yes. I cannot remember. Is it unsigned? Oh, if it's unsigned, then we have to use JCI instead of JLI. Thank you. There we go. All right, so I just saved the code. It is untested. Okay, so if this code is untested, I probably should make a note of that. Okay, so I'm gonna say this part is not tested because I that means I need to test it later. All right, so we get to the then branch. Okay, so this is the then branch, and we just have to kind of do this part here. Um, we calculate the right hand side and then store it to the left hand side. So for the sake of time, I'm not gonna do the full explanation anymore. So I'm gonna be a little bit terse here. F underscore ppn add ad ldaa ldea, and then we have ldi. Hmm, we don't have enough registers. Okay, that's all right. So ldia f underscore pn add ad ldaa ldi c node p next add ac st a b. Okay, so now I can halt again. Okay, I think that so when we halt, okay, this is basically doing line 18. So now you have to go back to the C code and ask, okay, what exactly is that doing? So you just track down, okay, this is ppn, this is what ppn is pointing to. So that means the right hand side of the assignment on line 18 should be 0. And then you look at the left hand side, this is pn, it points to n1. N1's p next is supposed to be changed to a 0, 0. So the change that we should observe is having this 0 put exactly here, which is at location 0e. In other words, I should observe location 0e being changed to 0, 0. And I'm going to run the program, okay, at this point to test it, okay, to see if that works. So I may not be able to finish this code today, so we'll have to kind of finish it on Thursday. So let's go ahead and test it. Okay, there we go. And then go back to the C code and location. Oh, that is not good. JZI to F then 0. Okay, did I forget to save the code? Okay, the code is not working the way it's supposed to because at location F then 0. Okay, I forgot to save. Classic. If most of the time the code doesn't work is only because I did not save the code before trying to run it, it's a minor irritation. Okay, so now we can give it a try, take a look, okay, because the last memory update should be location FE getting a 0, 0. All right, we got that. This is how I think you should be writing the code. Okay. Um, it is tedious. Okay. It is tedious, but you get a hang of things. Okay. You also get a but better understanding of how to implement the C code using assembly instructions. Okay. So I think that's, yes, go ahead. So FE still has a value of 0, 0 at this point. Yes. Yep. Say again. We are changing the P next of N1. So what we ended up doing is the P next of N1 now gets 0, 0. So that's the update that we saw. Say again. So the P first is our head pointer. That has not changed yet. So P first is still 0, 0. The whiteboard is reflecting all the changes that we're making. So right now P first has not changed. So we are gonna you know do something, we'll continue with the coding. So we are now done with line 18 of the C code. It's time to move on to line 19. Okay. So line 19 wants PN. Okay. And I don't have PN already saved. That's okay. We'll just kind of do it the hard way. We just redo everything from scratch. Okay. So add AD, LDAA. So that should be PN on the right hand side. And then we have to store that to whatever PPN is pointing to. So that's PPN, add a BD, LDBB, LDBB, um, and then we're gonna store it to that location. So that's PPN, not where it points to. So we need a STB, uh, the right hand side is in register A. There we go. Okay. So now we're going to put another halt instruction here. Okay, well, we use the same halt instruction, but we need to know exactly what is going to happen before we can check it, right? So we look at this picture, okay? We look at where ppm points to, which is location FE, and it has a value of 0, 0. So we are storing to the location FE. So now the next question is, what is the right-hand side? It is PN. PN is the address of N1, which is 0E. So this is where we update the head pointer. Okay, so that means, at this point, I am overwriting this 0, 0 so that it becomes 0E. That is what we should be observing. Location FE updates to the value of 0E. Okay, so make sure I save the code this time, okay, because I keep forgetting that. Okay, there we go. And then we go back to the other tab here, run the code again. There we go. And then we go back here and it just keep scrolling down. And sure enough, location FE is now updated to 0E. This is confirmation that I got the second line in the then branch done. And then we go back here, okay, go back to the source code, and now we should get the third line done. So the third line is not too big of a deal because all we are doing is we are storing ppn into result. ppn itself, okay, the value of ppn is still in register B. So all we are trying to do is to specify a return value of um, in the in register B. If you want to shortcut the whole thing and not to have to specify result, I suppose you can. Okay, you can do a CPR AB because that will basically just return a value of whatever is in register B, and register B currently has the value of ppn, so that would become the return value of the whole thing. All right. So we are going to give that a try. Okay. All right. So we can give this a try. The the My hesitation is to give this a try. We have to basically unlock the function so that it actually returns. So I'm gonna have to unlock this halt instruction, let it actually return, and then the only way we can tell whether this works or not is to put a halt instruction here. And then we have to specify what A is supposed to be, and A is supposed to be whatever PPN is, and PPN was what? Uh, PPN was the address of P first, so that would be the address of P first, which is supposed to be in the assembly code. That should be FE in hexadecimal. Okay. Yes, I know I just said a mumble a whole bunch of stuff that some of you may not catch up, but that's why the whole thing is recorded. Okay, so when you re-watch it in slow mo, try to catch everything that I just said. Okay. All right. So this is my suspicion, and we'll see if the program works the way that it is supposed to up to this point. Okay. So we have to go back to make sure we save the code. There we go. And then run it again. We got 3 minutes. So if I can get the then part completely done today, on Thursday, getting the else part done, should not be uh, too big of a deal. All right. So we are now saying that register A is supposed to be PPN. So now we look up, how we update register A, and the very last time we updated is indeed FE. So it has the return value specified correctly. So this is a verification of the entire then branch of the C code is now done. So let me go back to the C code here. So which also means on Thursday, okay, I can push it a little bit and try to do it today, do the recursive call, but I won't do it, okay, because we just don't have enough time to explain it correctly. So on Thursday, what we'll do is we are going to handle the recursive call, okay. Now, the most important part when you're dealing with anything that is recursive is to make sure the base case works first. In other words, when it's not supposed to do a recursion, make sure that case is working 100%, okay, before you try to implement the recursive call. Because if you cannot be sure that the base case is handled correctly and you try to implement the recursive call, it might just end up doing an unlimited or not ending and endless. It might end up with an endless recursion because you're not handling the base case correctly. So the most important part is to get the base case handled correctly first. And so that you don't have any doubt in your mind that if I'm calling correctly, it should work. And then with that in mind, then you can try to implement the recursive call, because the only bug that can cause your program not to work is the recursive call itself. The base case is already done. So that means on Thursday, what we'll do is simply to implement line 24. Line 24 will take 10 minutes at the most to implement. But to test it is a whole different thing. Okay, how do we test the code that is recursive? You kind of have to do it kind of one step at a time. So we have to unlock some of the other code over here so that we have to place a second call. The first call is never recursive, so you cannot just use the first call to debug the recursive portion. With all that said, okay, I'm gonna release the lab for tonight, and most of you will be kind of happy and unhappy about the arrangement tonight. I'll explain. Everything about me is, I guess, paradoxical. There's a good part, there's a bad part. All right. So this is the good part. Okay. You can see how it only has 3 points associated with it. So even if you don't do it, you're not going to lose a lot of points. Uh, the access code is node, okay, Node, but it has a second part which is due next uh, Tuesday. So next Tuesday is when you need to turn in the actual code corresponding to something that is also implemented recursively. Okay, and that one has a double recursion. Okay, so on Thursday, so if I were you, I would do something about this code before Thursday. Okay, I would get the conditional statement done, make sure you have access to everything and make the right decision, and not quite to get to the recursive part. Okay, and then after that, then you can go ahead and implement the recursive part, because as I said, the most difficult part and the most important part is the non-recursive nature of the code. Okay, so do not try to do anything recursively first. Do the base case. If that works, then the recursive part follows pretty easily. Okay, so that's it. Okay, I will see you guys at the lab. And yep, there we go. And I do have today's lecture recorded. Okay, so and I will send the code to you right away because otherwise I would totally forget.